Grabando, grabando.
Hey, hi everyone. It's a pleasure for me present today the second part of the event. Professor Irena Lasiecka. Irena is a distinguished university professor of mathematics and chair of the mathematics department at the University of Memphis. She is also co-editor-in-chief of several journals, precisely two very important journals, Applied Mathematics and Optimization and Evolution Equation Control Theory. Lasiecka earned her PhD in 1975 from the University of Vassal. In 2014, she became a fellow of the American Mathematics Society for contribution to control of PDEs. Moreover, her areas of study are partial differential equations related with control theory, as I mentioned before. Today, Professor Lasiecka will give us this great opportunity to attend his lecture, Controlling Rapid Oscillation in Flow Structure Interaction. Thank you, Professor, for this nice opportunity and to stay here in our event.
Yeah, thank you very much for this glowing introduction. It's almost embarrassing to me. So I'm very happy to be here, and you guys had a great initiative to make it, possible for all of us to participate. That's great. So thank you very much to all of you for making this possible. So the topic I want to talk about, it's something that I've been working for a long time, in fact, with several collaborators, as you see in the list. So there are some of the results which are go back, to many years ago, but some of them are very, very recent, and somehow they wrap up the program of a controlling oscillations in a flow structure interaction, which is the main topic. I also want to acknowledge contribution of my collaborators, and we have here a long list. And probably Igor Chuyeshov is the one that I worked for many years on a book, and unfortunately he passed away, but he was a really great contributor to this area. Now, flow structure interaction is something that really it's ubiquitous in nature, and you can find application in aerodynamics, in medicine, in large space structures, and engineering. Okay, and I will show you some of the examples, of a specific physical problem when one would be interested in controlling these oscillations. What I should say is that sometimes we call it flutter. So what it is, these are sustained oscillations. So these are not oscillations that break down, but they are sustained and for a long time, and therefore, if prolonged, they might lead to the damage of a material and eventual collapse of the structures. But somehow are also very, positive, have positive effects when you want to harvest energy, like windmills. Okay. So flow structure interaction distinguish essentially two speed. It's a flow and structure. So it's a combination of the two interacting on the interface. And depending on the speed of the flow, okay, Mach number, we can talk about subsonic or supersonic. Here you have some examples of a supersonic interaction when you have these big jets, which are surrounded by the flow of gas. In the subsonic cases, you have a famous Tacoma Bridge, which, as we know, it collapsed because of sustained oscillations. Okay, and also you have in treatment of some medical conditions like apnea, when there is intake of the flow of gas, which is here, that creates oscillation of a facial palate and eventually might lead to very unpleasant consequences. Like snoring, obstructive sleep apnea, and other things. It's exactly right now recognized as a classical structure and flow interaction that is of interest to medical applications. Okay, and also in heart disease, you do have so-called ectopid beats of the heart, which are triggered by the interaction of the flow, okay, within the blood system. So here you can see what happened with a famous bridge. So these are interactions, sustained oscillations that eventually led to the breakage of the whole structure. You here instead in a civil engineering, you might have a building. So we had right now a big storm in Florida, as you know. So that's what was happening. And as a result of moving of a wind, of a strong wind, that structure changes the position, displaces, and might lead to a total collapse. Okay, in aeroelasticity, okay, this is a classical example when wings of the aeroplane are subjected to the flow of wind. Okay, on a positive side, you might have windmills which harvest energy, and you would like them to work properly. So again, good control of this oscillation is extremely important to be able to harvest a good thing to, on the other hand, to prevent the breakage as it is here, okay? So what is the basic program? And in fact, that was a program which has been for a long time put forward by several funding agencies and also groups of labs led by engineers like Eric Erdauer in Duke and Balakrishnan at UCLA. So what you would like to eliminate this flutter if it is possible. It is not always possible, but you can control a flutter speed, which means the speed at which the flutter begins, okay? And how do you control? Of course, you have to do something on the structure, which is a plate or shell, okay? In post-flutter harvesting, situation is opposite. You want this oscillation to be controlled and to remain because you are harvesting a flutter. Now, one thing that was noticed, as I mentioned, with a lot of lab experiments with wind tunnel, and people did realize that in fact wind or flow of gas can exhibit some stabilizing effect, even if the structure has no active dissipation. As that it was something, it was difficult to explain mathematically, because mathematically we know we have a dissipation, we can show how energy is stable, goes to zero, at which rate. So I think that most people here in this audience are familiar with that kind of a program. Here instead, there is no dissipation. Nevertheless, there is some stabilizing effect coming from the wind. So the first thing for us was to understand where does it come from and how can we describe in mathematical terms and how to exploit this thing for flutter suppression. And what I'm talking about, these are pictures, you know, that are exactly based on experiment and wind tunnel. And also there is a review paper by Joe McKenna in AMS Notices when he was doing also some numerical experiments on a much more, on ODE model, much more simplified. And what is happening is that you do have some sort of a stabilizing effect of the wind, but eventually it stabilizes to something that oscillates. You see, like you see here, oscillations remain, so the flutter remains. So that's a basic situation what nature gives you. Stabilizes a bit, but it remains sustained. Oscillations are sustained. Okay. Instead, what one would like to do, one would like to bring this oscillation down to either zero or some stationary point that would remain within the dynamic. So that's an ultimate goal, if possible. It's not always possible. So let me just go back to the model, which is the most simple model for the given problem. And it's already had all the features that we really want to study. And that model should be credited to Erdauer many years ago when he was studying fluttering plates. Okay, plate is here, this omega, this you see here, dark gray object, which is in the upper half plane, x, y, z, z is positive, okay? And there are two variables. M is a Mach number, and we call it this U, capital U equal 1. It's normalized speed of sound because that parameter is going to be all the time and is very, very important. We have n-perturb flow of gas. It's flowing in a negative x direction, okay? So that's what it is. That's what really it's here. By phi of x, y, z, and t, we call velocity potential at a point, okay? And q, x, y, and t, it's a vertical displacement of the plate. So oscillations, what is of interest to us really from physical point of view are oscillation of the plate, but they are subjected to this flow. That's why this is an interacting system. It's a couple system, 3D with 2D. on an interface. Okay. Now, these equations are of hyperbolic type, and I'm going to emphasize this over and over because it's very important. Why it is important? Because in the past there was some modeling, in fact, in NASA, which is a laboratory here in US, in Langley, when they were working on some whole Helios. And the modeling was was of parabolic type. So they were looking at the plate as having some structural strong damping. Okay, strong damping means in mathematical terms that you have analytic semigroup and you have a spectrum which asymptotically has a good behavior in the left complex plane. And then it looks good from stability point of view because if there is any instability, it would be finite dimensional because you can eliminate just finitely many unstable modes. So what was happening based on this idea and calculations, people were doing essentially providing algorithms for the model. And this model collapsed. It was a famous collapse in 2002. And it was hard to understand what was wrong. And what was wrong was very simple, that the modeling of a by strongly damped plate was incorrect for that particular situation, because these are light and thin structures. They have a lot of hyperbolicity. Therefore, the spectrum is not really like in parabolic case. Spectrum is close to the imaginary axis. So therefore, any sort of a control of finitely many eigenvalues provides bad control for the high modes that they are not seen in the algorithm. Okay, and this one's the ones that created the collapse. So at the end of the day, it was agreed that we need to have a hyperbolic model. And that's what I'm going to emphasize. Okay, so what is needed? A good model. Analysis of this model, then you want to do experiment in the lab and make sure that it's consistent with analysis. And then you go into computational analysis and algorithms for control. So that's a basic program that one would like to follow. So in this particular talk, what I would like to do, I would like to, of course, we start with a model, and I emphasize more strongly that this is hyperbolic and hyperbolic-like with an interface. And questions asked are of that of stability, robustness, and long-time behavior. And there is a lot of previous work which was on the regularized parabolic-like models, and they do not work. What does it mean they don't work? You can prove theorems of existence of solutions, okay? Or also convergence of the energy to some stationary state, but they do not correspond to this physical phenomena of a flutter because precisely of parabolic effect. So the main result which I would like to present would be a result on a well-posed dynamical system, stability and long-time behavior. So what we'll be able to show is that we have a global attractors, but for the structure only, not for the wind. Instead, for the whole structure, wind and structure, we can control the flutter, okay, by obtaining so-called strong stability to an equilibria under certain conditions and under the control, okay? So what is interesting is that global attractors for the structure only will tell you that long-time behavior of a structure is reduced to finite dimensional one, okay? But it's not necessarily eigenfunction mode. That's the whole point, okay? You have a special structure. And for this, you don't need any control, you need analysis. But once you are there, you need to introduce a control in order to eliminate the flutter. And that is very important to emphasize. And the fact that the global attractors for the structure do exist is because of a strong nonlinearity, okay? Otherwise, we will not have that result, okay? So let me just look at the model. So the model in a simplest case, it's a combination of flow of gas, which is Euler equation in three dimensions for density and velocity V and pressure P. So we have equation of mass, equation of momentum, which is coupled with a structure which is dynamic nonlinear elasticity. Okay, nonlinearity here is represented by von Karman bracket with Airy stress function. I will talk about this a little bit more. And structure is ignited by the pressure which is created from the wind. Okay, so that comes from the first equation. So this is a basic model, but if you want to linearize this model around a stable profile, so I take here in 3 dimensions just an unstable profile, capital U, 0 and 0, so that's the velocity of the wind. And we assume that it's viscous irrotational, so velocity is proportional to the gradient of the flow, and barotropic, so we have relation between density and pressure. Then this model has a very simple structure in two variables. One is so-called elastic potential psi, which is nothing else but material derivative applied to velocity potential phi of the flow, okay? So these are two variables, psi and phi, and look how simple is the flow equation. Flow equation is just written as a hyperbolic system, but with respect to this material derivative of the variable. And that is coupled with a structure, which means that this structure is ignited by elastic potential of the flow. So the right-hand side, but restricted to the boundary in 3 dimensions, so it becomes just omega, ignites the structure. On the other hand, flow itself is ignited by displacement of the structure, and this is via boundary conditions imposed on the flow. So typical boundary condition will be flow tangency Neumann, which means Neumann data are given as a material derivative of displacement, or Kuta-Yukovsky so-called mixed boundary conditions, which are more complicated. I will not here bother you with this because a lot of, it's a kind of a Zaremba problem, and it has been, work has been done, but it's more complicated, definitely. So let's think of a classical Neumann that we have a displacement and 0 outside omega, outside the wing. For the structure, depending on application, you might have a clamp-free or hinge boundary condition. So here, probably people are familiar. And which boundary condition to choose depends on application. For example, when you want to study bridge, then should be a Neumann and structure should be free and hinge on the side, okay? When we want to study wing of the aeroplane, in the aeroplane, then the flow has to be modeled by Kuta-Yukovsky, which means pressure is of the wing and structure is free or hinged. So these are all combinations of the boundary conditions, okay? So what we want to understand, first of all, guided by the experiment from NASA and Aeroforce, okay, to show stabilizing effect of the flow on the structure. So we do nothing from point of view of control. Model has no active dissipation, but there is some stability discovered by experimental study. Knowing this, our plan is the following. First of all, we want to have a generation of nonlinear evolution. So we have dynamical system in so-called finite energy space. And then we'll be able to show that we have a uniform attraction of structural, so of plate solution only to a finite dimensional set. And then we can get a strong stability to equilibrium of the whole thing. So it means flutter is eliminated when velocity, when the speed is subsonic. Okay, for supersonic, there are counterexamples. This cannot be done. So right now this problem is still open whether and how, under which condition you can do the same thing. As I said, what was done in the past, a lot of work has been published, but they were involving a regularizing model of parabolic type. And as I mentioned, this is too much regularity in the solution, and this does not represent as a particular experimental model that we are under. There's no stabilizing effect shown by the flow itself, okay? Because there is a stabilization by strong damping, but this is not exactly a phenomena that we want to study. Too much diffusion. So at this point, the following conclusion should be reached, okay? That flow does not stabilize a regularized model. So it means essentially we cannot see this beneficial effect of the flow itself, which is confirmed by the experiment. Regularized model yield smoother solution by adding one derivative to to the model and making some nonlinearities compact. So simplifies the analysis of well-posedness, but it's not physical for that problem. Instead, the original model brings a lot of interesting mathematics. It is harmonic analysis. And we deal with so-called non-dissipative dynamical system, when you cannot work with an Lyapunov function because there is no dissipation law, as you see. Okay, and of course you do not have a compactness, which is a typical thing that you would like to have when studying attractors within the context of a dynamical system. So give rise to the new techniques, and these new techniques are in the area of harmonic and microlocal analysis, and some spaces of Hardy type. And most importantly, dynamical system theory has to be developed for non-dissipative systems. So let me go back to the model written in a way that probably you will find more familiar. So the first equation is the structural equation with nonlinearity. It's driven by the elastic potential, which is here on the right-hand side. And the flow itself, it's a modified wave equation. You can see this way, but it's with respect to this material derivative with the Neumann data, which are driven by velocity, by oscillation, by vertical oscillation of the plate. So you have two operators, which are sort of a material derivative, applied to the flow and applied to the plate. And as you see from that structure, there is probably some cancellation when you do formal integration by parts, because you have the same operator with the opposite signs. So you multiply the first equation by time derivative of u, and second one by time derivative of phi, and you will see that these effects simply will cancel, will not be visible in energy calculation. And on the other hand, they are critical for the behavior of our problem. So that's something to be careful when energy methods really don't give you much of insight of it's like a black box, what's going on inside. I should say that here very important aspect is the fact that we have a von Karman nonlinearity, because that's what really explains why we have this stabilizing effect of the flow on the structure by reducing to finite dimension. And one of the difficulty was to find a good estimate for that von Karman bracket, which gives you good regularity property. Like here it's written on the last line that any stress function is bounded from H2 to W2 infinity, which means the second derivative, it's a multiplier. So it gives a lot of benefits in doing calculation. And this is versus the old result of Lyon-Sierlet and other like Nese, when we knew only that any stress function had less than 3 derivatives in L2 space, which was not giving you really result as needed, 2 derivatives in L infinity. So it was essentially a missing 2 epsilons. So this result, I will not have time probably to go over, but it requires it requires theory of Hardy spaces, and that kind of a joint work with Tatar for many years, which is all the result in some sense, but it's very critical when we study this particular problem. Now, if you want to look from point of view of energy, so it means that you multiply the one equation by velocity of the plate and the velocity of the flow, and you look at the energies. What is characteristic here, if you look at the flow energy, you see this minus sign, and there is a u square. So you see that in this way, flow energy is not necessarily positive, because that quantity here can be quite negative. So therefore, you get that if you add everything together, you get a constant, but that doesn't mean anything. That's a black box that, everything, okay, it adds to the constant, but there are some singularities between each quantities, and energy itself is not a topological measure of a solution. And that's a difficulty. You have to break the damn box and see exactly what's going on for the solution. But that's the first thing that if you do by standard, say, energy methods. So as I said, energy balances retain. However, this balance doesn't tell you a word about dissipation. In addition, there is a loss of ellipticity for u greater than 1. Okay, so there is a hidden dissipation in the model, and we want to discover. That's our goal. So let me just state main result in a qualitative way, before I go to quantization. And that is that we'll be able to show existence and Hadamard-Weld posedness of finite energy solution. By this I mean these energy quantities, which were introduced a moment ago, are going to be finite. The solutions are bounded for all time. So it's like you saw in the picture. You have sustained oscillation. And here the critical role is of nonlinearity, would be false for linearization. Okay, when you have a speed Mach number different than 1, which means it's except for transonic speed, we don't have any dissipation on the structure. We show that this solution converges to a finite dimensional and smooth set. So this is given by essentially the wind alone plus nonlinearity. These are two effects of nonlinearity and of the wind. We don't control, we just watch, and that's what is happening. However, next step is to eliminate the flutter. So then we introduce feedback control implemented on the structure, and under certain conditions that it requires only subsonic velocity at this stage, we can eliminate with structural feedback control. So control enters after we reduce structural solution to finite dimensional set. So here is a statement of the existence of a nonlinear semigroup. Okay, this is a joint work with Tuyashov and Webster. And as you see, solutions are bounded. So it gets a description of a good dynamical system. The result is here critical. It's a finite dimensionality of attracting set, but for structure only. So we can show that if you look at the plate equation in a classical topology, which will be 2 derivatives for displacement and L2 for velocity, then there exists a compact set which has 1 derivative more, okay, which is of finite fractal dimension, and this set attracts all the structural solutions, okay? For compactly supported initial data, what does it mean? Since our flow is in upper half plane, what we are interested only effects, okay, on some finite set, compact set with respect to the space, which is realistic, which is what we want physically. However, the set which we obtain here of finite fractal dimension can be chaotic, okay? Have limit cycled periodic orbits, and this was shown by experimental and numerical work by Dowell and Howell from Carnegie Mellon. So just to give you an idea, so what we are doing, we are taking all initial data which are bounded, then we take a semi-group corresponding to the whole flow, we restrict to the structure, and this guy is converging to the attractor. Okay, so that's a result. And that attractor is smooth, but potentially chaotic. Okay, so what we obtain here is this kind of a behavior. Okay, so they are sustained oscillations, okay, chaotic, periodic, of a structural component, of a vertical plate component. And here I have also computation of a non-trivial set of an attraction. So the next part of a program is to obtain strong stability. So we want to show that semi-group of the representing both flow and structure is strongly stable. So what it means, you take initial data and you want to go to equilibrium in time. So in some sense, strong stability is the weakest, much weaker statement that attractor, but the difference is that result before refers to attractor for the structure only, and this is for the entire system. And that stability result has tremendous implication because it tells you that flutter can be eliminated, because we bring the whole system to the rest, okay? And amazingly, proof of that result really involves proving an attractiveness property for the structure. So it is kind of a very unusual strategy of proof, okay? And here is the result, and that requires a control. So here is the result, that if we look at the structure and we put a control which is with respect to velocity, time velocity, and this is ignition by the flow, okay? So this is a perturbation, so creates an instability. So we can show that as long as this is non-trivial, this function, say if you take a linear, so we have to be strictly positive, and it's important that we have a nonlinearity, we can show that in fact any solution of flow and structure converges to an equilibrium, okay? So any solution, dynamic solution, has a point in equilibrium set such that it converges to. So it means that flutter can be eliminated. So the consequence is that the flutter can be eliminated by applying a damping on the structure only, okay? So that's the first time one control effects. And nonlinear effects plus of effects of the wind are critical in first reducing the whole structural solution to finite dimension. So that result cannot be obtained without having information on the finite dimensionality of the structural attractor. So what it is here, you see that we get exactly solution converging to some stationary states. So flutter can be eliminated. So these are some other examples. And we get really stability. So these are just references regarding, as you see, some of them are pretty old, so the program has been for a long time, but I want to point it out most recent. In fact, this is 2024. This is joint work with Balakrishnan and Webster, and that really when we are able to finally solve the problem of strong stability, and I will say how, okay? But you have a lot of information also in older papers related to the model and other. So there is a Oberwolfach seminar volume, which was published again in 2018 with a model and also with some result. And most recently, we have a book, Fluids Under Control. This is edited by Bodnar, Galdi, and Nechasova, which has this most recent result on the time talking about strong stability, how to obtain this result, okay? So what are the tools to obtain much of the result? First of all, for existence of dynamical system, we need some compensated compactness because of this Airy stress function. And to do this, we need to work within Lasiecka spaces. So Lasiecka spaces are really a tool, doesn't come up at all in the result because we have finite energy. However, in the process of doing, we need to refer to some of the properties. And most important, there was a necessity of developing abstract result for non-dissipative dynamical systems. So what does it mean non-dissipative? That you don't have a nice energy relation with the damping, which is a kind of a starting point for almost all papers on dynamical system, okay? And for this, we have to, what is happening is that, in fact, one can reduce this model to a system with delay. So delay comes quite naturally, and therefore you have to study results for a delay system. And here I leave this thing for you. So you have some references for the tools. And as I said, the last paper is the one that essentially completes the model. And here I just want to mention that all the result in joint work with Tataru related to von Karman Airy stress function is so critical here when we're able to really discover this Airy stress function sharp regularity, which allows to really run the program. The previous result was giving you von Karman bracket in some distributional sense in a negative Sobolev space, or Airy stress function could have 3 plus epsilon derivatives, but that's not enough to conclude that what we want to have, okay? So I will not go here over, but it's important that to really have in mind how the proof goes over. And I'll just very quickly remind you the problem was that any stress function, which is defined by the von Karman bracket in the following way. First result, it's showing that this bracket itself takes H2 into Hardy space H1. What is easy to show that it takes into L1 because these are two derivatives, but it's not enough. You need H sub 1, which is Hardy space. And to do this, you need some compensation, okay? And compensation is due to the structure of the bracket. And then you refer to some elliptic theory on Hardy spaces, Lasiecka spaces, and use critical Sobolev embeddings to get the result. So these are a posteriori just points, but they are repeated here in several occasions in trying to get the estimates for nonlinearity. Okay, so I say here compensated compactness. It's a bit technical. I leave this thing for you. It goes back to the Kaufman and Meyer estimates of compensation for bilinear form. Magic cancellation, I skip this. Okay, so that is important, very important tool used. And what you want to do, you want to show that there is an attractor for the structure. And how do you do this? You have to show asymptotic smoothness, okay? So so-called compensated compactness criteria, which many of you know and use. It's a sort of a, if you don't have a compactness of the trajectories, okay, which could come either from parabolicity or from compactness of a nonlinear term, then you have some sort of a possibility for compensating compactness, which is reflected by this inequality. The distance between two trajectories can be made arbitrarily small, plus some functional, which is almost compact. So it has a convergence in terms of iterated limit rather than limit itself. So this is kind of a new criteria, relatively new, which is here very important, and it applies to von Karman bracket with this information I told you, okay? And for people who are not perhaps familiar, a bounded set is global attractor if it is invariant and uniformly attracted. If we have absorbing set and asymptotic smoothness, we do have a compact global attractor, okay? And there is also another definition of quasi-stability, which is an estimate for the system, and this is more demanding than just asymptotic smoothness, but what it does, it implies a finite dimensionality of attractor and smoothness and reduces PDE to ODE asymptotically. So these are the tools that we've been using. Yeah? And now back to flow structure interaction, what we are doing. Remember, energies as defined before were not really very helpful because they were depending on they were not topologically informative. So you rewrite this energy in a different way, only with respect to the variables flow, elastic and flow potential. And then what you have, you don't have energy constant, but you have energy polluted by this term, which clearly shows lack of dissipation and lack of compactness. And so therefore, the rest of the treatment is how to deal with this perturbation. And that involves a lot of trace regularity for the flow, which is a solution to hyperbolic equation because it is a priori and bounded on energy space, okay? So we obtain this result of a finite fractal dimension. I would like to say, just to explain where is the trick, why do we get eventually this wind creates a dissipation? Because if you solve for three-dimensional Kirchhoff plate flow for phi, asymptotically for time t large enough, you can write your plate in the following way. So here is a nonlinear term, but what flow contributes is this term ut, ux, and this delay term, okay? So in essence, you see that this u sub t, which was not in the model, becomes a gift from the wind. But it is, of course, counteracted by strong instability written by right-hand side. So therefore, the final game is how to take advantage of this dissipative term versus non-dissipative. but at least you see that there is something to play with, okay? And I'm going to, so I would say that as a result of that, we do get a global attractor exists for the structure. It is smooth and finite dimensional. And this is owing to the nonlinear effects in the wind. And the dynamic on the structure might be fluttering and chaotic. How to eliminate the flutter? Control theory enters. And here we put a control in terms of a damping, okay? And we show that in fact, that solution converges to the stationary state. So flutter, when U is less than 1, can be eliminated forever. What is critical here in this proof is the fact that plate has an isotropic symbol, and we use microlocal analysis because the lack of regularity for a Neumann dynamic map is in a characteristic sector, as you know. But in this sector, we have exactly an isotropy of a plate that allows us to take advantage of it. And that was something that was discovered very recently and eventually settles the problem. I know my time is over, so I'm not going to go much to this. Just concluding, flutter can be eliminated by applying damping on the structure, and flow has stabilizing effect with no damping at all. Solutions are driven to finite dimensional set. PD dynamic is reduced to ODE, but structure of the set without control can be chaotic and periodic. And stabilizing effect of the flow can be exhibited only for a correct model and regularized, and so it means without regularization. There are many problems here under still investigation, transonic case, other boundary conditions. This is a joint work also with Filippo Gazzola, Denis Bonner on a free clamp, which is again very, very difficult configuration for the plate. And we have also results on a shell model, okay? So there are a lot of things which are open, but this is at least a basic understanding of the phenomena. So I want to thank you for your attention, and sorry for taking a bit longer, and here references. Okay, thank you.
Thank you very much, Professor Lasiecka. Well, let's open for questions and comments. We have time for questions and comments. Please, Juan, can you open the microphone?
Yes, it's open.
Okay, the microphone is open. Everyone also can write in the chat. Okay, feel free to ask questions or comments for Professor Irena. Okay, one message. Yes, it's open the microphone. Yes, the chat as well. You can write in the chat.
Irena, you may say where the micro-local analysis come into this discussion.
Oh, you come in several places. But
Yeah, with the wave equation, hyperbolic and stuff.
yeah,
You could mention these sectors.
Okay, so this is the work, the most recent one, when eventually we were able to show this thing. So what was the problem? The problem was to show that asymptotic attractor, that exponential attractor is smooth. That is usually an open problem because we know that attractor can be smooth, but exponential attractor, because you want to have a good rate of attraction to the system, are not necessarily smooth because they are only positively invariant. So here you have to go back to the structure of the solution itself, of the coupling, and coupling is where? Coupling is a wave equation with the Neumann data, which enters with L2 data. Now we do know very well that in dimension higher than 1, dynamic Neumann problem does not have a finite energy solution, doesn't have H1, L2 solutions, okay? So there is no way to overcome this thing. But data comes from the structure which with velocity U sub t, which is just L2, no more than that. as that was the issue, that we couldn't get even any sort of a fixed point, because you start losing derivatives. So what is happening, and that's a microlocal analysis, that this defect of a regularity, it's only in characteristic sector for the waves, okay? But in this characteristic sector, we have a plate, and plate has variables u sub t, and which is L2, but also second derivative in space. And plate symbol is anisotropic, because two derivatives in space corresponds to one derivative in time. But in this particular sector, that's good enough, because in essence, we are gaining two derivatives in space. And all we have, and therefore we can use, but this has to be done microlocally, because it's not true for the whole system. And that's what really was able to, we're able to show smoothness of the exponential attractor, and the whole program for a strong stability has been working, okay? So in a sense, we can say that it goes back to some study of linear hyperbolic structures, but here it's really very specific to the model when you combine plate and wave, okay? Just in a linear context, because that was a difficulty.
Okay, thank you. Lucero send nice talk, Irena. Sorry, I have to leave. I have teaching now. Okay. Hey, thank you very much, Irena, for this nice talk. Let's thank you again, Irena.
Thank you.